Yes, I'm very glad to the steering committee. Yeah, even though I should have done more than I would actually. Thanks for braving the sort of Monday morning rain, coming and listen to my talk. So all the stuff that Ravina has said, those are the things that distract me from doing my research actually. So I'm not that far off. I want to thank Ravina and the executive committee for inviting me for this plenary talk. So I'm going to share something about my view. Okay, I'm not going to pretend I'm a flexible electronics person. I'm actually, much of my career has been in effectively microelectronics. But I'm going to tell a story that to tell you, to convince you that, sort of this field is converging. And it's converging, and the story is really about material science. And I think the folks here who are working on solving the problems on materials becomes very important. Okay, so to start, I think since I need material science talk, we talk about periodic table, right? So this is a sort of microelectronics that where microelectronics have been in terms of material usage, right? So you look at the 70s when sort of electronics started to happen, post 60s, you only use a certain selected few elements of the periodic table. As microelectronics advance, more and more of the elements of the periodic table is used. Today, they're not only used as elemental compound, but also compounds of these is used. So today, virtually everything on the periodic table is used, other than, or even including the gases, but definitely not including the radioactive stuff, right? So that's where electronics have been. So, and the reason for that is because microelectronics is such an aggressive area, and the focus is to really enhance performance and functionality, that every opportunity that material provides, we will be leveraging. Okay, so let's talk about the parallel universe, right? So the parallel universe is flexible electronics. So this is something from a paper that I've taken up. Also starting in the 70s and now to today, right? We also, as a flexible electronics community, use a lot of different materials, and that's been evolving. Obviously, the early 70s and 80s, we talk about conductive polymers. Then sort of focus went towards organics, TFTs to build active devices, and inorganic TFTs, oxide semiconductors, and then nanomaterials, graphenes and CNTs, and then now there are polymers that self-heal and potentially used for energy scavenging. So same story, different universe. That there's an increasing use and need for new functional materials. Right. So those are two universes that kind of happens in parallel. So I'm going to just lay on the table what my message would be upfront, right? And I'll come back to it. So what I'm going to say is that typically, as complexity goes up, the thermal budget tends to go down. You get to understand what that means. And then on chip scale electronics, the focus is really that there's a lot of high thermal budget materials to process at high temperature. And because they need for high performance, but then the functionality is typically very narrow. Okay? Now, in the area of large area electronics, which is where flexible electronics sits, typically we head towards lower thermal budget because of the materials we use. And obviously that comes with lower performance, but that broadens the functionality tremendously. So the key is how do you combine both, right? And there's a coming need to combine both. And then the heterogeneous integration is the key, and that's where a new set of innovations will have to be developed. And that will give us high performance and broad functionality. I think Professor Morocco has just said that in RF, for instance, they are eagerly looking for solutions for flexible RFs. And then I think increasingly important will be these low thermal budget material innovations. Okay, so these are what I'm going to tell you. I'm going to tell you now, and then I'm going to tell the story and frame this, right? So why thermal budget, and why semiconductors is such a high thermal budget process? It's really about defect management. So if you look at crystals, any defect that form is actually today detrimental to the performance of solid state electronics. So these defects are point defect, dislocations, and dangling bonds, right? So these are effectively breaking, to some extent, the bonding energy of between the atoms. And in semiconductors, because things are so small, you cannot really tolerate this kind of defects. And so silicon typically processed at thousands of degrees C needs to maintain that temperature. And any change to the crystalline property needs to be healed using this kind of temperature. That's why, morphization and thermal annealing is the key. So this is really about defect management. Now, why is this important? Because as you move away from crystalline material, this defect formation energy and healing energy will change, and that's the opportunity. So this, the way I summarize electronics usually, I look at size scale, right? So this is feature scale on the horizontal axis and then size scale on the vertical, right? So transistors occupy the lowest portion of that, right? And that's driven by Moore's law. Now, typically you have low defectivity, high crystalline material as I mentioned. So because you need a high material stability. And silicon transistor processing typically is about 700 to 1000 degrees C. Now the way you would actually rationalize this is that you look at two things, which is thermal stability and mechanical stiffness. At the order of the electronics semiconductors, really mechanical stiffness is not so important. But you look at those two plots, melting at temperature and bond energy, silicon and germanium typically in gigapascals of Young modulus. The bond energy is fairly high, usually hundreds of kilojoules per mole, and melting temperature is close to 1000 degrees. Right, so these materials you cannot typically make usually at room temperature. And if you modify them at room temperature, they are going to be very defective and not going to be giving you the performance. Right. So now let's move on and look at what's above, right? So you have transistors, then you have wires to connect them, so they interconnect. And typically, this starts to go into lower thermal budget because you're dealing with metal. And copper is one of them. And now the processing temperature drops from 1000 degrees, 800 degrees Celsius to 500 degrees Celsius. Right? Again, if you look at this, you have lower stiffness, you have, again, atoms move much quicker, more readily, and then you have to maintain them, and this limits the thermal budget again. Right? So let's move up some more. Okay, now we have transistors that are wired, and now the wired chips are now bound together into this packaging. This packaging now starts to activate, uses polymers, right? So these can't stand anything beyond 200 degrees Celsius, right? And because same thing again, you look at your access polymers at the bottom, you need a little bit more flexibility in terms of packaging. You're moving away from crystalline material, you're moving away from metal, you're moving towards polymer, and that means that processing temperature drops down to 200 degrees C. Right? And then the moving compound and all that needs to be low temperature. Right? So this is starting to get into the domain of flexible electronics where polymers are being used in synthetic compounds. Now you go to the board level, right? So now you started all the way from silicon transistors all the way now up to a board, PCB board. Again, limited by 200 degrees Celsius, assembly and operations become important. And then if you look at zooming into the board area, you have this big area beyond the centimeter scale to the meter scale. Now we talk about large area electronics, and now that there is more interaction with the environment. Now mechanical form factor becomes important. And also the temperature requirements are also lower. So these are examples, right? I listed that Ben's work on sensors for robotics and for wearables. You have flexible RF antennas that needs to conform and needs to be folded so it can be brought into space. And then you have a large area display, right? But all these require something very unique. It needs the performance of rigid semiconductors, but the form factor of flexible electronics coming together. So I think this hybrid flexible flex hybrid approach is what it is. And I'll get into more of that. So that determines sort of this spectrum, right? Beyond the board, they're going much bigger. Thermal budget obviously limited by the lowest temperature material they use, which typically are the flexible materials. So that is sort of the spectrum, all the way from the bottom, the little transistors, all the way up to these flexible electronics. And then you need these low thermal budget functional materials to kind of span. And then as you get beyond the centimeter scale, then the form factor and mechanical integration become important. So this binds the several levels of electronics, right? So here's my pitch to you, right? So the pitch is the following. There is a convergence of this, and I'll go into some of the work to talk about that. As the need for electronics and increases, I mean, nobody's without that. You have basically rigid semiconductor materials that are scaling that's continue pushing this, and you hear a lot of this with now driven by AI. In fact, AI drives a certain aspect of system integration. In fact, you now need chips to be packaged all together so to reduce latency of access. But what I'm going to tell you also is that the methods that are used in the traditional flexible electronics, the additive-based processing, and the additive-based manipulating materials are also becoming important because form factor is increasingly important as well. And so this is what I claim to be sort of a new convergence that the two universes that we had before, which is all this, rigid semiconductor, high temperature process, thermal budget stuff, and this low thermal budget stuff with printed and inks are coming together and converging, and that's the claim. So I'm going to talk about some of these things that I'm exploring in my lab, right? So let's look at this back-end line to connect and fed it out, or say, well, okay, this is the domain of classical semiconductors. So what has that got to do with flexible electronics? But we'll talk about this in a moment. So there's a lot of excitement around GPUs and high bandwidth memory and AI, right? And these things operate at thousands of watts kind of chip, and it makes NVIDIA very rich effectively. So this is what one of them looks like. And what's unique about this is that you can see that there are three parts to it. There's the memory part, there's a CPU die, and then there's something called an interposer, which is the interconnect, right? And then the goal here is move the memory closer to the compute unit. And the reason for that is because a lot of these AI models use a lot of data bandwidth in crunching numbers. And a lot of the energy is expensed at bringing data in and out of compute. So more and more you need this integration of memory and compute getting closer and closer together. And it used to be on a PCB board, that's no longer good, so now they put it on this thing called an interposer, which is actually a chip itself, the bottom, and then soon you're going to stack memory on top of compute. And so that's where things are heading in terms of rigid electronics, right? So bring the memory on top of chips itself, and then stacking into something that looks like effectively a skyscraper city of chips. So this is where microelectronics is heading quickly, right? Now, one of the things that we look at is when you do stacking of materials on top of chips, then the issue is, as I mentioned before, that the interconnect thermal budget is lower than that of silicon. So if you're going to put active devices in the back end of line in the interconnect layer, they have to be processed at below 500 degrees Celsius. That's a problem because silicon guys typically don't know how to do that. How do you build transistors up there? But the flexible people have been doing that all along, right? With oxide semiconductors and all that stuff. So that's coming in. That's interesting. And the reason for that, why you need that is because copper is a fast diffuser. So if you process the high temperature, you just get out of the wire and start traveling between the dielectric between the wires, and it causes reliability issue. So this is the number one. One of the detriment of having copper may cause high temperature. So if you want to put active devices at the back end, you really need to observe the thermal budget. So if you look at this chart, it summarizes the type of materials you can use, right? So you can use silicon, which is bad because as I mentioned, you're 800 degrees to 1000 degrees C. germanium could bring it down a little bit. But carbon nanotubes, 2D materials, and oxide semiconductors become interesting. And that is sort of shaping where everybody is starting to look at, right? And these materials are traditionally flexible electronics materials, right? So why it now become important is because we want to bring it in to the back end of line of chips. So low process temperature, some properties, electronic properties we'll talk about, bring them exciting options. So let's look at oxide semiconductor. Okay, so this is traditionally a material that's used for display, backplane, right? And now the question is, can we use this on actually a chip? So the material is somewhat foreign to a lot of semiconductor folks because the transport properties depends on the defect of the system, vacancies, the vacancy mediated transport, so the carrier density is a function of the transport. So we have to engineer the defect density in the system, the vacancies. So we've done quite a lot of work. Okay, so one of the things to look at is that you look at the mobility of this device. Flexible electronics, TFTs, usually the mobility is in the single to double digits, centimeters square per volt second. Now, semiconductors, rigid semiconductor mobilities go up in the hundreds to 1,000 centimeters square. So there's a gap. So in order for these devices to be usable in a logic in terms of semiconductor, it has to get into the hundreds of centimeters square per volt second. So this is what we've been working on as CM mobility, and we've, for instance, optimizing material for indium gallium zinc oxide, we can get the mobilities up into the hundreds. Now this is as far as it can go probably, but it's good enough to be used as a logic device. And obviously you need the whole function to be okay. So the key is now to stabilize this material in the back end line, right? So we've done a lot of material, fundamental material study to understand how that can be done. So this is the device that we built. It's a indium gallium zinc oxide device. It has a stabilizing layer, interfacial layer of indium tin oxide, right? And this indium tin oxide stabilizes it such that the heat resistance of the material is minimal. It's processed on high K metal gate. Typically in flexible electronics, it's done on silicon dioxide, but here it's hafnium oxide. You can see that the mobility is in the hundreds centimeters per second, and it has good transfer characteristics, right? So it's up by at least 10 to 100x from what we started with. So now this old material that's been used for flexible electronics is finding new life in silicon electronics, right? As a way to use it. So how do we use this? Well, you can stack them on top of silicon, and you build circuits on top of them. This is some of the things that we do. They can be stable. We build memories. So this is a device that's quite unique. It's actually an ISO device which is bottom gated, but the top side is actually a ferroelectric, having zirconium. Right? These are typically not what flexible electronic people will be doing. But when you do that, this device has very good hundreds. It goes a million cycles of cycling. You can build. You can have analog ferroelectric switching. So you now have this memory device that could be switched to store weights of neurodense, and then you can build them on top of CMOS as a reconfigurable FPGA switch, which you can't do before because this is intrinsically low thermal budget. You can use that to rewire chips effectively. That's what we look at, right? So now a traditional flexible electronic material gets modified and souped up and now using for chips potentially. Okay. So let's so seven and 2D materials are another hot area for both semiconductors as well, traditional semiconductors as well as flexible electronics. Okay, so the vision for electronics in general is that these things are 2D materials that are low thermal budget again, so they can be built. You can stack them sequentially on top of CMOS chips to increase memory density, right? So this is an example, this is Mario's work actually, I'd like to highlight it, nice work. Very promising, where they show that they can actually do HPN, which is 2D material dielectric based, 2D material on top of CMOS. So this is what we all aspire to do, in terms of combine nanomaterials like these things that are low thermal budget on top of silicon chips. So this is more and more people will be starting to do this, and this is an exciting area. Okay, so there's a lot of work to enhance the materials. So these materials intrinsically, like I said, because they are low thermal budget, they cannot be defects and stuff like that has to be managed in a different way. Here we're enhanced drive current of 100x for such devices using room temperature plasma oxidation. So you cannot use high temperature plasma oxidation because these are done at back end similarly for flexible electronics. Right, we've done without solution processable, so this is starting to look like flexible electronics again. Right, you can sonicate crystal grade fragments of it. We build high endurance resistant RAM, which is a form of memory. And why we do this? Well, in fact, this is being a lot of oxide-based resistant RAM. And the reason for that is it turns out to be that these flakes actually create something called population network, and it gives you ability to tune effective length of they call it filaments and endurance. So it gives you an additional degree of freedom that you would not have got if you have just used traditional semiconductor materials. Okay. So we stack them as this solution base on top of a chip. You can see that these are 3 layers of memory that is spin coated on the top of chips, right? You can see that they are metal, 2D material, metal, 2D material. You can access them just like what you did in a stack. So you can increase memory capacity quite dramatically here. So other hobbies of mine, I mean, to look deeper into 2D materials. So I talked about these 2-terminal resistive RAM. And now you can make them into transistors, right? Transistors used to be, well, I said in the start of this, transistors have to be stable. Nothing moves, and they have very narrow functionality. Now, what if they are not actually, but you can control them? So these are examples where we create a memory transistor where actually the material that we use is 2D material, because it's done at room temperature. You can introduce defects in them, and the defects can move. Now we control these defects. Now what is interesting is that these defects are also dopants in the system. So you can imagine that a transistor with dopants that you can move around by feet. So this is a transistor that's kind of fluid in a way defined. Now in traditional silicon transistors, dopants don't move around. They're not allowed to move because their processes are 1000 degrees C and they stay put once you activate them. Here, the dopants move around. When you start moving around, you get all these strange hysteresis. Now the question is, can you control them? The answer is yes. You control them, and this transistor not only create different type of memory states, but you can actually have more memory states in the 2-terminal device. Okay. So the example with this, so in a 2-terminal device, you move atoms around or vacancies to create this filament which creates this memory. But in a MEMS transistor, what's interesting is you're moving these defects around, and these defects effectively are the dopants transistors, and they move in stage charge region of the transistors, right? So these are a lot more physics involved in operating these devices because the defects actually interact with the stage charge in the device itself. So now you have a device that has even greater functionality. So the fact that the point I make is that high thermal budget, high stability, narrow functionality. As you start comfortable moving out of that comfort zone into low stability material, you want to play with defects, you get higher and broader functionality, even though with a little bit less performance. Okay, so we do a device like that, we created a floating gate for it. So now this is 2 memory into 1, right? And what can you do with this? Well, you can create a device that can act like a, it can act like a five synapse, means it can inhibit as well as excite connection. So you can build neural networks for it where the same device can be used for enhancing connection when you learn something. It can also inhibit in the same single device. And there's a paper that we wrote talking about this. And then we can make sort of the feature extraction property of the eye, endocrine cells within optical within the eye. And basically in the eye, instead of just traditional neural nets basically just learn and intensifies connections, here is one that not only intensifies but also sort of weakens other connections. And a single device can do both. And the reason why it can do both is because of what I said, which is that it can now manipulate those effects back and forth, changing the property of the transistors. On top of that, you can remember it switches polarity because of the material itself. We also implemented two-dimensional materials onto photonics. So here we actually added two-dimensional, spin-coated two-dimensional materials onto a activation function of a photonic neural net, and then we use it for nonlinear functions. So we don't go into all the details of this, but what I'm saying is that these materials enhance functionality, and you can add them in later, and not at the start of doing the device. Obviously, you can print them, so we have the ability to print the aerosol jet is one approach we can do. Screen printing is another one, because they can be formulated in inks, and you can print them on. This is no big news for anybody who contracts with electronics. Okay, so now we move into this regime beyond the packaging, right, under the board level. And a little bit about hybrid flexible electronics. So there's a fundamental motivation for this, right? So in hybrid flexible electronics, obviously we have rigid components under there, sensors, display, antenna, stuff. I think it was already mentioned at the starting of this session that these new areas beyond the rigid electronics add a lot of functionality in the RF space. Now, why do we do this? Why not just do everything flexible? Why you don't need to, for one thing. Second is, a more important part is that you need a trade-off in performance and size. So rigid electronics, very stable, high performance, so you need to leverage that for signal processing, right? But those rigid electronics cannot be easily extended in terms of area coverage. So you start using all these sort of flexible electronics to do the area coverage. And those two things combine together. Now it's obviously brings forth its own unique set of challenges when it comes to integrating these two types of materials. So we dabbled in some of these as well. So this is one example where we drew an ECG patch that embedded a sort of a tiny chip on board with flexible interconnect, right? Because that would be big enough so that you be connected to the body. So we built the whole thing in an elastomer matrix. We use liquid metal as an interconnect material, but you can obviously see where the problem will come. There are huge differences in Young's modulus, and coupling them becomes a big issue. So you needed the electronics because the signal processing we cannot do this with just organic transistors. It's very difficult. It's hard to do even an offset that kind of thing. So I have to go back to silicon, and so we have to design a signal processing unit for this. But the key now is how do we interface the flexible stuff with the rigid stuff. That's the source of innovation. And here, obviously, we have to design it such that it does couple well with the flexible electronics. And obviously, the size differences gives you the fan out, fan in, interconnect problem. But once you get it done, we have a lot of advantages. So here, left and right, one is the rigid board version of the one that's in the flexible part. Performance are equivalent, right? But here are things that you can't do with a rigid board. Obviously, you can't stretch it. You cannot submerge in liquid easily. And so these are things that the properties of flexible electronics become superior to rigid electronics, just by changing the way the substrate of the electronics is done. But obviously, it creates a new set of problems. This is another work that we've done, and this to make a point, which is, we needed a gesture sensing glove, right? So, but we want to do it using capacitive sensing. So these are a bunch of capacitors that sense how the feel around the hands are moving, right? And it has to be coupled with advanced electronics. So we developed a signal processing unit that is asynchronous. That means it collects all the capacitive sensing data asynchronously, anytime, anywhere. And then it has to be transmitted to a phone for edge processing, because the glove has to be connected somewhere. It's flexible on your hand, but the wires running off your body will not be good. So you have to be wireless communication with a phone. So what this says, well, you have to combine three things: flexible sensors and wires for data collection, high performance electronics for signal transmission, and then obviously with all of this stuff going on, there's going to be noise and variability, and that's where the algorithm comes in and help with advanced AI machine learning model. So there's no one solution to this. It has to be a combination of different things, and each one of them does the best. So things that flexible stuff can do that rigid can't. For instance, triboelectric. So a lot of triboelectric generation now is at very small scale. Here is what we've done is we created a elastomer foam. It's very simple to do. It's embedded with liquid metal to increase the dielectric constant of the foam itself. But it's really templated off salt, actually, rock salt. We created this cavity using salt and dissolved it. And what it does is that it gives you this way of generating simple electric charges when the foam gets compressed. So these are things that rigid and small electronics can't do, but you can do that with something big like this. So you obviously could generate a very high amount of current and voltages, and obviously that is to be managed by voltage management, power management hardware. Okay, so I come back to this slide, right? So we kind of walk through the scale. Right? I gave you examples of materials that semiconductor is using that's borrowing from the knowledge of flexible electronics, low thermal budget. There's actually enormous opportunity for innovation in this space. And I think the two community needs to come together to start innovating on the material science of it. Right? Obviously, the form factor becomes increasingly more important as you get above the packaging level. And that's because it's interacting with the environment, interacting with people. So that brings me to Shine. So it's a center that we started back in 2018. It's to look at combining this into a single facility. So we bring state-of-the-art semiconductor rigid electronic processing capability to marry it with traditional additive-based flexible electronic capability. And why we're doing that is because there's quite a bit of new problems to solve, really. Like some of these tools here are traditional chip packaging capability. And we actually integrate these capabilities with front-end of line materials-based research capability also. Deposition, the film deposition, the ALDs, together with packaging, and then finally together with some aspects of printed electronics and additive-based manufacturing. So a lot of these tools are all operating at low thermal budget. Right? Let's see forward. So coming back to this, Shine kind of operates in this space, right? Where basically they interconnect, and the problem that we're trying to solve is extending from heterogeneous chiplet integration, that means from chip packaging point of view, all the way to hybrid electronics, heterogeneous packaging capability. So this is where flexible electronics come in. And I'll show you some examples of projects that we look at, right? So this is one example where we look at bonding a laser onto a chiplet. So this is photonic interconnect. So the next generation AI chips will slowly move away from electronic interconnect to photonic interconnect. And photonic interconnect operates at the millimeter of size scale to bring memory in. So laser integration becomes important. So this is one aspect of our capability here is to create bonded new annealing-based components onto the chip itself. In this case, the laser. This is work by a collaborator from NTU, not collaborator, in fact, part of Shine, Seldom's group. And so they look at the problem of interfacing interconnect with rigid electronics. So he developed a biphasic interface of soft interconnect and packaging. So the traditional skills of using flexible electronics now come into chip packaging as well, as you increase the level. Then thermal. So in the past, thermal was never the issue. So this is a new problem for hybrid flexible electronics, right? So if you want the performance of a rigid chip to do the processing, you have to deal with the heat that it produces. So now we're working on effectively novel thermal mitigation schemes on flexible electronics. In this case, it's a phase change material built into the flexible electronics itself that dissipates heat and stores them so that it doesn't degrade the soft components. So coming back to this message that I'd like to share is that as the integration gets more complex, you are going to get more lower thermal budget. That's the key, right? From transistors all the way up. So we have to deal with that. And then I think using high performance silicon is needed because of signal processing, but that's high performance narrow functionality. Now you would go into all these new materials, the trade-off is that they're lower thermal budget, but they are also lower performance, but it enhances your functionality immensely. So the key is how do you marry the two? Because you want the best of all worlds, right? So high performance, and that's where the hybrid flexible electronics come in. And the innovations on lower thermal budget material is now much needed for both rigid electronics as well as flexible electronics. So with that, I come back to this, and the claim is that this convergence is happening, and we need the communities to work closely together to create that innovation. With that, I would thank my group, who's done a lot of research work here, and then in Singapore, we are funded by the Singapore government as well as the US government on many of the projects we do, and as well as defense partners. With that, I would say thank you. Yep.